intended to introduce the single sample t-test and contrast it with the one sample z-test. So first we need to start by talking about a new set of distributions, the t-distributions. And we use t-distributions when the means when we know the population mean, but we don't know the population standard deviation. So for the distribution of means, we don't know what the population parameters are, other than the mean. So what the t-distribution does is it allows us to estimate a population standard deviation from a sample. So remember that our sample standard deviation is computed by using this formula where we have our individual scores, subtracting the mean, we square those scores, and then we sum them all together, so we get our sums of squares, and we divide by the number of scores. So it's the average squared deviations from the mean, and that's for a sample. When we want to estimate the population standard deviation, we have to make an adjustment. And so we need to use a new formula. Note that we use a lowercase s to denote the estimated population standard deviation. And we use our sample data to estimate what we think that variability would be in the population. Because if we randomly selected from the population of interest, it should represent that population. However, we do know that it tends to underestimate our population, and so we have a little correction here of n minus 1. So for t-tests, we now need to use s, the estimated population standard deviation, in our denominator. So in order for us to do this, this should look pretty familiar. We calculate our sample mean, we use that sample mean in the corrected standard deviation formula, so we take each individual score, subtract out the mean, we square that value, and then we add all the squares together. And then we divide by the number of scores in our sample minus 1. So here's an example. We've got our sample mean of 12.4. If we subtract it from each of these individual scores, we get these values. And then we square those values, and we can sum those values together and get 35.2. And notice that we have 5 scores, so our denominator should be 5 minus 1. We get 8.8, and that value, let's make a quick correction here, and that value needs to be taken to the square root, and so once we take the square root, we get 2.97. So remember that that's really our standard deviation of the population, and when we compute any sort of comparison between means, we're using the standard error here. And so in order to get the standard error, this should look pretty familiar. Now we have S sub m, our estimated standard error, and we use our estimated standard deviation in the population, and again we divide by the square root of n. Now, a lot of people often get confused and think, oh, now I have to use n minus 1. When we are calculating the standard error, we use n. We've already made the correction, so we don't need to use n minus 1. And then for our t-statistic, here we have the mean that we're interested in, our population mean that we're comparing it to, and then we have our estimated standard error. So really the only change that we have at this point from the one sample z-test is how we get this standard error, because we're estimating it based on the sample, because we don't know what it is in actuality. So in order to calculate a t-statistic using the standard error, we can continue from our previous example. Remember, we calculated that estimated sample, our population standard deviation from the sample as 2.97. take the 2.97 and divide by the square root of 5, we find our standard error to be 1.33. If we assume that our population mean is 11, then we can calculate our t-statistic of 1.05. Now, like I said before, our t-statistic is a family of distributions. So there's another little bit that it's different based on the fact that we're only able to approximate a set of curves depending upon our sample size. So when the sample size increases, the standard deviation that we estimate based on our population, or based on our sample, for the population gets closer and closer to being the same as what the standard deviation is in the population, sigma. And the t-distribution and the z-distribution become more and more similar. So the t-distribution is assuming that shape of the z-distribution. So the t-distributions are a set of distributions that are based on differences between means. Because remember, we are comparing two different means. In the one sample t-test, we're comparing a sample mean to a population mean. And that part is in the numerator of our formula, the top part of our formula. So when I say that there's a family, I'm sure you've been wondering what that means. If you look at this set of normal curves, or they're not exactly normal curves because the shapes aren't quite there, but what we see is the purple one here, the standard normal z-distribution. This is the shape that we've been talking about for the z-test. And you'll notice that our distributions for t-tests are wider and flatter distributions. They're not quite as peaked. They have a lot more in the tail. So you can imagine that the 5% that falls in the tail would actually be adjusted based on that. So for a t-distribution that has about 30 people, you can see it is slightly different from our normal distribution, but the tail is not that much different. So once we kind of get to that 30 in our number, our sample size, then we actually have a lot better approximation of the normal distribution. Here, the teal colored one, or this blue one, our distribution is based on 8 individuals, and you can see that there's more in the tail. And then this last one, where we have a t-distribution based on 2 individuals, the tail's very fat. So you can imagine that our critical values would get shoved way out here towards the tails in order to have only 5%. Before we move on, let's have a little check your learning. So I want you to pause for a minute and answer the 2 following questions. When would you use a z-test? And when would you use a t-test? And you can give an example to yourself to kind of check what you're thinking. So if you said you would use a z-test when you're comparing a sample mean to a population mean, and you know both the population mean as well as the population standard deviation, then you are correct. The difference between a z-test and a t-test comes in when you don't know the sample, you don't know the population standard deviation. You could say maybe you'd be interested in finding out whether a group of students at a particular school is doing as well as the students in the state. If you know what all of the student standardized test scores are, then you probably would want to perform a z-test because you'd also likely be able to get that population standard deviation. But let's say that you don't have all the scores, and so then you'd have to do a t-test because you wouldn't know what that population standard deviation is. So in terms of hypothesis testing, this is just to introduce you to the single sample t-test. So we use this when we know the population mean, but not the standard deviation. And now we have a new thing that we need to use in order for us to understand which one of the t distributions, because they're a set of distributions, a family, we use. And we're introducing something called degrees of freedom. Let's say that we have 5 people in our sample. And we know the heights of the first 5 people in our sample. And we know that the average height in that sample is 5'6". So in order for us to make sure that we get a height of 5 feet 6 inches tall, we can have any value we want for the first 4 people in that sample. But that 5th person, in order for us to have a mean that's 5 feet 6 inches tall, that's going to be predetermined. So once you've got those first 4 scores set, or those first 4 heights, in order for us to have a mean of 5.6, then you know that you have to have a particular height in order for that to happen. So let's say you have a bunch of fairly short people, and their average is, an inch below 5.6. And if there's 5 people, well then you know that that last person in the sample, in order to counteract that set of scores where their average is 5.4, well, you'd have to have, or 5'4", you'd actually have to have somebody who's extremely tall to pull that up 2 inches. But you'd know exactly what that would need to be. So that's where degrees of freedom come in. The degrees of freedom are the number of scores that are free to vary. And in a single sample t-test, the degrees of freedom is n-1, where n is the sample size, so the number of people in your sample. Then what we do is we use the t-table, which you'll find in Appendix B of your textbook, and you look up in the first column the degrees of freedom. So if you had 5 people, 5 minus 1 is 4, so you know you have 4 degrees of freedom. And the t-table is much smaller. This is just an excerpt, but what you can see is that you have a set of one-tailed tests, and then you have a set of two-tailed tests. And here, this first row tells you the alpha level. 0.10, 0.05, and 0.01 are the 3 columns. So those are your choices. Generally, we use the 0.05 column, and usually we're using two-tailed tests. So if we have 4 degrees of freedom, and we're using an alpha of 0.05 for a two-tailed test, then our critical value will be 2.776. So basically you need to take the number of people in your sample, subtract 1, and that will give you degrees of freedom and tell you which row you need to use. And usually you're going to use a two-tailed test with alpha equals 0.05. So here's something for you to think about. Which do you think is more conservative, a one-tailed test or a two-tailed test? And you might want to pause for a moment and consider which one you think it might be. Okay, so if you said that you believed a two-tailed test was more conservative, then you were right, because it's harder to reject the null hypothesis with a two-tailed test. You can see that for alpha equals 0.05, we have a greater critical value than when it's a one-tailed test. So finally, let's talk about calculating the effect size. Remember, this is the effect size for a t-test, so we use the estimated standard deviation. It's basically the same as the effect size that we used for the z-test, but in the denominator, what we have instead of sigma is the estimated standard deviation. And if we go back to that example, well, there was an example earlier where we're talking about what is the number of sessions that an individual attends if they sign a contract versus not, then you can find that the effect size is 1.29. And the Cohen's interpretation conventions are the same as for the z-test, so this is a very large effect.